you'll find that psi as a function of phi must be given by this expression right here. So, and when you do this, you come up with a quantum number. So once you apply your boundary condition, a restriction will come up. And that restriction is that there's this quantum number m, which is going to be restricted to 0, plus or minus 1, plus or minus 2, and so on. So this is the quantum number that comes up in this expression. So m here is not the mass, it's a quantum number, okay? So sometimes you put m sub l there to make a distinction between that and mass. It's m sub l because it's a quantum number that's related to the angular momentum, as we'll see later. Now, how does the quantization come about? That comes about when you apply the boundary condition that psi at angle phi must be the same as psi at angle phi plus 2 pi. Why is that? If this is phi right here, where is phi plus 2 pi? Phi plus 2 pi is going to be that one, right? Phi plus 2 pi, and phi means this is referring to the same point. So this is a requirement for your psi. It has to be single valued. So phi and phi plus 2 pi refers to the same point. So we have to insist that the value of psi, when you plug in phi or phi plus 2 pi, must come out to be the same number. And when you do that, you come up with the quantization. Okay. Just like with what we did with the particle in a box. When we imposed the boundary conditions, we came up with the quantization. And so you should be able to verify also that the magnitude of the normalization constant n here is just 1 over square root of 2 pi. How do you do that? You just say that integral of psi star psi d phi from 0 to 2 pi must be equal to what number? 1, right? So by insisting on normalization, you'll be able to show that this normalization constant, the magnitude of this n, is going to be 1 over square root of 2 pi. So those are your wave functions. All right. So let's look at what these wave functions look like. Regardless of m, if you were to plot the magnitude of psi itself, then it's going to be a constant. Why is that? What's the magnitude of psi? That's just the square root of psi star psi, right? And what's the square root of psi star psi? Psi star would be n e to the negative I m phi, right? Actually, n star, right? Times psi itself is n times e to the I m phi. So that gives you square root of n star times n. What's e to the negative I m phi times e to the I m phi? E to the negative x, e to the x would be e to the 0, right? So that's just going to be times 1. So you can see that that's a constant. That means the probability of finding the particle anywhere on that circle is uniform. It's the same. So the probability density function is constant as a function of theta. Doesn't depend on, phi. Doesn't depend on phi. All right. So regardless of what the quantum number m is, it's equally probable to find the particle anywhere on that circle. So if I were to ask you, what is the probability of finding the particle between phi 0 and pi over 2? What integral would you have to write if you were to do this? You'd write integral of psi star psi d phi from what? 0 to pi over 2. So you plug in the expression. That's going to be n squared e to the negative I m phi e to the I m phi d phi from 0 to 2 pi, 0 to pi over 2. So that gives you what? That's just going to be integral. That's going to be magnitude of n squared. What's integral of d phi? That's just going to be phi, right? Because this is going to be 1. So phi evaluated from 0 to pi over 2. And that gives you, what's n, magnitude of n squared? What was magnitude of n? 1 over square root of 2 pi times pi over 2 minus 0. And this is to be, that's squared, right? So that's going to be 1 over 2 pi times pi over 2. And that cancels out pi. That gives you 1 pi. Kind of did this there. We didn't actually have to do this, right? We could have answered this question without actually doing the integration because 0 to pi over 2 is 1/4 of the full circle. And we've already shown that it was uniform throughout the entire circle. So 1/4 of the circle, probability of finding it is pi over 2. I mean 1/4. All right, what would it look like if we were just to plot the real part or the imaginary part? Well, what's the real part of your psi? This is n times cosine m phi plus I sine m phi, right? E to the I m phi is cosine m phi plus I sine m phi. So this thing right here, n times cosine m phi, this part right here, that's the real part of psi. So what would that look like? You plot it from, let's plot it from 0 to 2 pi. Real part of psi. Cosine 0 would be what's cosine 0? It's 1, right? And m is 0, so it's going to be, regardless of what phi is, it's going to be constant. It's just going to be n, right? Correct? Okay. What would it be if m equals 1? So it's n cosine 1 phi. So n cosine phi, what does that plot look like? The real part of psi anyway. Phi going from 0 to 2 pi, what does the cosine function look like? It's going to be n over here, right? And then it's going to go down. And it will complete one cycle in, one cycle is 2 pi, right? So let's see, it would go like so. That's one cycle. You'll notice the value here and the value here must be the same, right? Pi is single valued. All right. So what about m equals 1? What would that look like? 0 to 2 pi cosine n cosine 2 phi. So what's your wavelength here? Two pi over lambda is going to be equal to 2, right? So lambda is equal to This is 2 pi over lambda, right? It's equal to pi. So that's one cycle at pi. So there's from n right here, you have one cycle to get there. That's one cycle for the cosine function. And then you have another cycle right here. And again, the value of psi at 0 and at psi at 2 pi must be the same. So here you have 2 nodes, right? You have 1, 2, 3, 4 nodes for m equals 1. What about m equals negative 1? And cosine negative 2 phi. What would it look like? So this is the real part, right? This is the real part of psi. What's the imaginary part of psi going to look like? What is cosine of negative 2 phi? Cosine is an even function. It's still the same as cosine 2 phi. So the imaginary part is the same. Right? Remember, your imaginary part is sine m phi, right? But what if m equals, what about the imaginary part? I'm sorry, this is the real part of m equals negative. I got confused. Sorry about that. This is the real part. The real part of psi is the same whether it's m equals plus 1 or minus 1, right? Sorry about that. That's the real part. Both of these are the real parts. Now let's look at the imaginary parts. What would the imaginary part of psi look like for m equals 1? What's the imaginary part equal to? It's going to be sine pi, right? For m equals 1. So if you plot from 0 to 2 pi, what would it look like? Oh, I think I made a mistake here. This is m equals 2 now, huh? Sorry. This is m equals 2. Yeah. And this is the real part for m equals 2 and m equals negative 2. The same thing. Okay. So the real part is the same, regardless of whether your m is positive or negative. It's the imaginary part that's going to be different because your sine is an odd function. So if you had m equals 1, okay, let's plot that again. The imaginary part would be what? Sine function, right? And the wavelength for this is 2 pi, right? So this is the imaginary part of psi for m equals plus 1. What's the imaginary part for m equals negative 1? The imaginary part of psi when m is negative 1 would be negative sine. Yeah. So the two functions are not the same. Okay? So there's a difference between m equals plus 1 and m equals negative 1. They have the same magnitude, they have the same absolute value, okay, they have the same probability density, they have the same real parts, but their imaginary parts are different. The imaginary part of one is positive, the other if the imaginary part of one is positive, the other would be negative. Okay? So those are two, we say those are two linearly independent functions.